Let's have some fun with our new friend, the generating function. So the generating function, as you might recall from the previous video, is a function of x and t, which in case of the Bessel function takes the following form: exponential x over 2 t minus 1 over t. And by definition, the expansion coefficients, when we turn this into a Laurent series, are the Bessel functions of the first kind. So n minus infinity to plus infinity, j n x t to the power of n. Now, what I suggest you do is you pause the video and then, just for fun, take the partial derivative with respect to t and then use the definition of the generating function again and see if you can derive some useful properties of Bessel functions that way. So let's take the partial derivative, excuse me, with respect to t. So taking the partial derivative of the exponential, that gives us x over 2, and then t gives us 1. This becomes 1 over t squared. And then we have again the exponential x over 2 t minus 1 over t. Okay, so that's the left-hand side. And then for the right-hand side, taking the derivative with respect to t is rather straightforward, j n x, and then we here have n t to the power of n minus 1. Now, what do we see here is we see this exponential, and this exponential is actually the generating function. So what we can do now is substitute this equality here, this series expansion, back into that equation and then see what happens. So if we do that, we get x over 2, 1 plus 1 over t squared. And then we have the generating function equal to the sum of jn of x t to the power of n. So n going from minus infinity to plus infinity. And then we have the right-hand side again, summation n minus infinity to plus infinity, j n x n t to the power of n minus 1. Now, yeah, let's expand this thing a little bit. So this will become two series expansions here on the left-hand side. So let's see what happens. We have x over 2, and then we have the summation of j n t to the power of n. And then we have x over 2 and another summation. But there, because of this 1 over t squared, we have here jn t to the power of n minus 2. And then for the right-hand side, just copy what we had. We had a sum of jn n t to the power of n minus 1. So we basically have a sum of two series expansions on the left-hand side, a series expansion on the right-hand side. They both sum over the summation index n. In this particular case, that doesn't really matter that we use the same symbol for both. It only becomes tricky when you multiply series expansions. If you add series expansions like this, it's not that tricky. Now, but what we can do is, so on the left we have a series expansion, on the right we have a series expansion. We can just make sure that we identify the like powers of t, and then derive an equality between the left-hand side and the right-hand side for each particular power of t. So pause the video, do just that, identify a certain power of t, and then see if you can derive a recurrence relationship for different orders of Bessel functions. So in order to make it a little bit easier to identify the same powers of t here, we're going to make sure that everything is in a form like t to the power of n. So for the first term, that's already okay. So here we have the sum over n jn t to the power of n. But then for this guy over here, we have t to the power of n minus 2. So to make our life a little bit easier, we're going to introduce a new summation variable n prime, which is equal to n minus 2. So if we do that, well, if n runs from minus infinity to plus infinity, so will n prime, so that doesn't really matter. But then rather than having jn, n is equal to n prime plus 2. So this will become j n prime plus 2. And then we have t to the power of n prime. And now it's a lot easier to identify like powers of t. And then we play the same trick for the right-hand side here. But now we have n prime equal to n minus 1. So n prime will also run from minus infinity to plus infinity. Here we have a Bessel function of order n prime plus 1. And n here becomes n prime plus 1. And then we have t to the power of n prime. Now, the structure, the similarity becomes very obvious now. If you really want to make sure that it's exactly the same, you can again go from n prime to n, but that doesn't really matter. Now it's very obvious, very easy to identify like powers of t. And then because these two series expansions need to be the same, that means that the coefficients of each t to the n should be the same. And then we can just read here from that expression that means that x over 2 j n of x plus x over 2 j n plus 2 of x, that is equal to n plus 1 j n plus 1 of x. So that's a relationship between Bessel functions of 3 successive orders. To make things a little bit more symmetric here, we can go from n plus 1 to n. So we're just going to decrease the order of the Bessel function here a little bit. So then we have, if we factor out x over 2, then we have jn minus 1. So just decreasing the order by 1. Rather than n plus 2, we have now n plus 1. Okay. So now this thing becomes a little bit more balanced, plus 1 and minus 1 as opposed to 0 and 2. And then rather than having n plus 1 on the right-hand side, we have just n. Okay. The way this is typically written is by bringing x over 2 to the right-hand side. So we have that jn minus 1 of x plus jn plus 1 of x is equal to 2n over x jnx. And here we have a recurrence relationship between different orders of Bessel functions. So this will turn out to be a useful equation to prove other equations, but also this is used from time to time numerically. When you want to calculate Bessel functions of very high order, then people typically calculate with the regular method the Bessel function of order 0 and 1, and then they work their way up to a very high order, 2, 3, 4, 5, 6, to however high order you want, using this recurrence relationship, because it turns out that this is often a little bit more stable numerically. This just shows you here that by making use of the generating function and by doing a little bit of exploration, you can derive all sorts of useful equations for the Bessel functions.